So, ladies and gentlemen, nice to see you again. And I have pleasure to introduce Professor Bartosz Kwaśniewski, a very good specialist from system algebra, especially Joachim Kunz algebra and generalization. And today, he is professor at Białystok University and worked there all the times. And now he will be talk to us about Groupoid Banach Algebras. Please, Professor Kwaśniewski.
Thanks for the introduction, and thanks the organizers for having me and for organization of all this here. It's an honor and pleasure to be here. So today I will talk about joint work with these two young gentlemen. So this is Krzysztof Bardadyn and Andrew McKee, who are also based at the University of Białystok. So the main motivation for this talk comes from the success of the theory of groupoid sister algebras. This is a very rich theory which also covers a large class of sister algebras. In particular, all simple classifiable sister algebras have groupoid models. But also it has a lot of applications to different fields, in particular weighted sister algebras generated by weighted composition operators on L2 spaces often have groupoid models, and using that one can infer a lot about the spectra of single operators. And in fact, I wrote a paper with Krzysztof on that subject, and perhaps I should have been talking about this paper, but unfortunately I decided to talk about our ongoing project, which kind of was motivated. We wanted to generalize these theorems from groupoid sister algebras to more general Banach algebras, so then maybe we could apply it to weighted composition operators acting on different Banach spaces, most notably LP spaces. But the problem is that the theory of groupoid Banach algebra does not exist. So there are some definitions in some cases. There are some particular cases due mostly to Phillips that are very well studied, like LP version of Kunz algebras. But apart from that, there are no general results. So my main goal today would be to try to persuade you that there is a really nice framework where we can not only give nice definitions, but also prove these nice theorems. Okay. So throughout my talk, X will denote a locally compact Hausdorff space. So equivalently, we may look at it as this nice commutative Banach algebra of continuous functions that vanish at infinity. And we could consider the real case or the complex case, but I will assume that everything is complex just for simplicity here. So the action will take place on this algebra, on this space, and the nicest action, maybe what you can consider, is an action of a discrete group. So this is nothing but homomorphism from the group to the group of homeomorphisms of the space X. But we want to have a little more than that, so we want to generalize this. And there are essentially two ways of generalizing this: to étale groupoids with the unit space X, or to inverse semigroup actions. And these two points of view are in a sense equivalent, and sorry for that, but I will need like 2 slides to explain this a little bit, this equivalence. Groupoid can be defined as a small category with all arrows invertible. So you should view this G as a set of arrows between points of the space X. And we can compose those arrows whenever the target and domain agrees. This composition is associative, and each arrow has an inverse. And we put a topology on this, so everything is continuous. And in fact, we assume that the groupoid is étale, which means that the range and domain maps are local homeomorphisms, meaning locally injective open maps. So the fibers are discrete of these maps. And one more important notion in this business is bisection. So by bisection, I mean an open subset of the groupoid such that the domain and range map restricted to the set are injective. And since we assume they are open, so these are like homeomorphism from U to their ranges. So an étale groupoid is such groupoid which is covered by such bisections. So bisections Any bisection induces a partial homeomorphism. So in a natural manner, so if you take an arrow from this U, it is uniquely determined either by its domain on range, so this partial homeomorphism just takes the domain and sends it to the range. So this is basic notion, and if you don't like groupoids, but you have nothing against group actions, then you may stick to this example. So if H is just a group action by homeomorphisms, then the associated étale groupoids can be identified with this product space. So then each arrow in the groupoid denoted here, this is tricky, by xt starts with x and ends with ht of x, where ht is this homeomorphism given by the group action. So then we can consider these layers. They are natural bisections, and they induce this h of t. So looking at these bisections, we can recover the group action. In fact, these bisections form naturally a group. In general, bisections in an étale groupoid, they do not form a group, they form an inverse semigroup. So let me recall that an inverse semigroup is just a semigroup such that any element has a unique generalized inverse, and generalized inverse means this relation. So of course, a group is an inverse semigroup. We can take the inverse as this star, but this class is more general. And the model example of an inverse semigroup is an inverse semigroup of partial homeomorphisms. So partial homeomorphism is a homeomorphism between two open sets. So we have the set D and H of D and a homeomorphism between them. So there is naturally defined composition of such things. So we just take the composition on the largest domain that the composition makes sense. And this becomes a semigroup, and in fact, this is an inverse semigroup because we have natural star operation here. So every inverse semigroup is a sub-semigroup of this inverse semigroup. So this is one thing that is good to remember. And so it is natural to define an inverse semigroup action as a semigroup homomorphism from this S to this semigroup, this universal model partial homeomorphism of X. Okay, so how is it related to the groupoid? Because whenever we have a groupoid, these bisections, denoted here by this G, form naturally an inverse semigroup. So the composition is given by the composition of arrows, and the star is given by the inverse of arrows. And not only this is an inverse semigroup, but it acts naturally on the unit space by these partial homeomorphisms that are induced by these bisections. So this is also kind of universal example, meaning that every inverse semigroup action factors through this action given by bisections. And this is given by the transformation. So whenever you have an inverse semigroup action here, then we can form this transformation groupoid, generalizing the previous example. And so we may view this action as given by bisection of this groupoid. And each groupoid is the transformation groupoid of an inverse semigroup action. Okay. So now we want to represent these inverse semigroups, and then whenever one sees this relation here above, one immediately recalls what is a partial isometry in a Hilbert space, the standard notion. But there is a really nice generalization this to Banach spaces due Mustafa Mbehta. So what is that? So a partial isometry on a Banach space is a contractive operator such that it admits a contractive generalized inverse. So when E is a Hilbert space, this reduces to the standard notion of a partial isometry. But when E is an arbitrary Banach space, it may be that even this T star exists. It is not unique. That is why Mbehta also introduced the notion of Moore-Penrose partial isometry. So if we assume, in addition to that this TT star and T star T, which are projections, contractive projections, are Hermitian operators, then this T star is unique if it exists, because then this is a Moore-Penrose generalized inverse. So, yeah, Hermitian operator on Banach space, this can be characterized as those whose, for instance, the exponential group consists of contractive elements, and this is the same as numerical range is real. And this is related to the work of Phillips, who constructed these LP versions of Kunz algebras, and he used their spatial partial isometries. So what is that? So Phillips considered semi-finite measures, and everything was separable, but if we want to deal with general case, we may always assume that our measure is localizable. So any measure space can be transformed in a canonical way to a localizable measure space, and this does not change the LP space as a Banach space. So when we view these LP spaces as Banach spaces, we may always assume that the measure is localizable. And localizable means that the Radon-Nikodym theorem holds there. So for these measures, the Banach-Lamperti theorem holds, and Banach-Lamperti theorem says that every invertible isometry is a weighted composition operator. So in fact, using this theorem, we can generalize it to characterize these Moore-Penrose partial isometries. I mean, so Banach-Lamperti theorem holds for all p's different than 2. So if you have a p different than 2, then we can prove this theorem that every Moore-Penrose partial isometry is a weighted composition operator of this form. So basically, this T phi is a composition operator. So phi is a partial. This is a set isomorphism, but between like two measurable sets. So formally, this is a set isomorphism between sigma algebras. And this omega is just a unimodal map, so this is like a factor which is not very important. So what I would like you to remember is that this partial isometries are here in this context weighted composition operators, and Phillips didn't know the work of Bechta, so he defined spatial partial isometries as operators of this form, just given by the formula. But now we have this nice connection with Bechta definition. Okay, no questions? So let us turn to the main object of the talk. What should be the Groupoid Banach algebra? So if I recall, G is an étale groupoid with locally compact Hausdorff unit space. So this immediately implies that G itself is locally compact, but only locally Hausdorff. So it not necessarily has to be Hausdorff, but for the sake of simplicity, we may assume that it is Hausdorff. Then the space of compactly supported continuous functions on G can be also viewed as a linear span of functions, of compactly supported functions living on bisections. In the non-Hausdorff case, Alan Kohn taught us that this should be the definition then. Okay, but this is maybe not that important. So this space is naturally a star algebra with natural convolution given by this multiplication from the groupoid and natural involution. So we want to now define the Banach algebra. So what should be the norm? So perhaps the most famous norm is the so-called I norm introduced by Hahn a long time ago. So you should view this as a kind of generalization of L1 norm in a group. So if the unit space X is a singleton, so G is a group then domain maps and range maps are the same, where we don't have to write this maximum. So this is just a L1 norm. So in the general groupoid, what you can do, you can use either domain map or range map. Then you can take maximum over these units, the unit space, and then what you can do, you can take maximum. So this is a natural, nice norm on this space CC of G. But it turned out from our analysis that there is one more natural norm that we took as that norm. So there is the largest submultiplicative norm, what we denote by max, on the CC of G, such that it agrees with the supremum norm on each of these subspaces of functions living on bisections. So there is an explicit formula for this norm, but what I would like you to remember is that we have this, so far we have, how many? 1, 2, 3, 5 norms. So this norm is not submultiplicative, these are. And all these norms agree with the supremum norm on these spaces, but this is the largest one. So we take this as the universal norm And so we define the groupoid Banach algebra as the completion of CC of G in this maximal norm. In order to relate to other constructions that exist in the literature, one can also associate Banach groupoid algebras to any family of representations. Maybe it is worth just to look at classes where representations are given by a fixed class of Banach spaces. So for any class of fixed Banach spaces, we denote this Fe of G. The groupoid Banach algebra, which is universal with respect to representations on this Banach spaces. And here, by representation, I always mean a contractive homomorphism. So for instance, if you take for this class to be the class of Hilbert spaces, one recovers the usual groupoid sister algebra. If we take for this class LP spaces, then we recover what should be called the groupoid LP operator algebra. Okay, so the definition is nice, but what can we do with it? Can we prove theorems? And the main tool of our analysis is the kind of, I would call it inverse semigroup disintegration theorem. So any groupoid can be viewed as a transformation groupoid for some inverse semigroup action. So this is not an assumption. This is just we pick one action and we'll want to look at this G now from this point of view, from the inverse semigroup point of view. So I recall that this means that we have this homeomorphism between open sets, and we have this composition law, and etc. I assume my inverse semigroup is unital, so we have also this. Okay. So there is a very natural notion of a covariant representation of an inverse semigroup action. So what is that? So by a covariant representation of this action, I mean a pair of two representations. So pi is a representation of our Banach algebra C0 of X, and V is a representation of an inverse semigroup. And like I told you, by representations I always mean contractive homomorphism. So this is homomorphism, semigroup homomorphism into contractive elements, which means that automatically all these guys are partial isometries in Mbeta sense. And we need to relate this to representations. So the first relation is a standard thing if you know like representations of groups or actions of groups. So this is this commutation relation. So whenever we want to move this VT from left to right, we can do that, but then we need to put this HT star here in order for having everything covariant. So this is like a kind of standard relation, but in order to deal, I mean, we deal with partial isometries rather than invertible isometries, so we also need to take care of the range. And so this relation implies that the range of this partial isometry contains this guy, so we assume in addition that it is contained in this, so in a sense we assume in the presence of 1, 2 just means that the range of VT is this thing. So this kind of natural generalization of a covariant representation of a group action, and what is important about that we have a bijective, natural bijective correspondence between representations of our universal groupoid Banach algebra and covariant representations of these inverse semigroup actions. So the formula is as follows. So this means that our ranges of our representations are always given by representation of C0 of X, which has really nice properties, is very good Banach algebra, and a bunch of partial isometries, which are also often very good. So using this, we can prove several results. I will just tell you two. So first, let me try to apply this to this LP operator algebra business. So for any P from 1 to infinity, we define this LP universal groupoid Banach algebra as this Fe, where is the class of all LP spaces. So this means that these are universal Banach algebras with respect to representations on some LP spaces. And we may always assume that mu is localizable. So this agrees with a definition of Eusebio Gardella and Martino Lupini, who define it in a different way using representations of groupoids, which is kind of sophisticated tool in Hilbert space case developed by Jean Renaud. and it works only in a separable case. It is really nice, but in a sense, it is much more complicated than what I showed you. And they also use Han norm rather than the max norm that we introduced, but the definition agrees, and this also follows from this theorem that we proved. So we have these really nice estimates on these universal norms. So first of all, I mean, these extreme cases, L1 and L-infinity, we have like concrete formulas. So these are exactly these guys that appeared in the definition of Han norm. So Han norm is a maximum of this and that. So these are universal norms for L1 and for L-infinity. And for other P's, we have these really nice estimates. And in order to prove this, we in fact had to use a lot of operator theory. For the case P equal 2, this is known. But for different cases, we needed to apply lots of other results. And in particular, for P different than 2 and different than 1 and infinity, we can show that essentially all representations are given by covariant representations such that the representation of the algebra acts by multiplication operators. So it rather has range in L-infinity rather than in this thing. And the representation of the inverse semigroup acts by spatial partial isometries. So spatial partial isometries are those introduced by Phillips. I recall these are those weighted composition operators. So in particular, it tells us that, that all these LP groupoid algebras, they are necessarily generated by weighted composition operators. This is one thing. A second thing, it explains why Chris Phillips considered this spatial partial isometry. So I think this is an advantage because he just considers spatial partial isometries, and this seems awkward. Why? Why to restrict to that? And now having this theorem, we see that if we want to have groupoid models for these Banach algebras, they have to be given by spatial partial isometry. So this is not an assumption, this just follows from the structure. Okay. No questions? So I would like to present the final result, the simplicity result, which was in standing open problems mentioned by several authors. But in order to do that, I need to introduce more algebras, reduced versions of algebras that you have seen. So reduced objects are usually defined by some concrete representations. And for this LP business, we have really natural representations. So for each P, we have a representation of our universal LP groupoid algebra on this small LP of G. And this is given just by this convolution. The formula is exactly like in the convolution. So in a sense, this is given by the action of the groupoid on itself, which means that this is the right notion of a regular representation. And so it is natural to define this reduced LP operator algebra as the range of this representation. So this is what we do. We define this as this. So these are concrete operators in this concrete operator space. So let me summarize what happened so far, because we had a lot of different algebras. So all these algebras on the picture are completions of CC of G. So this is the universal one. This one is given by this Han norm I. So as we proved, all these guys lie below. So we have all these arrows here are contractive homomorphisms. So it turns out that this universal F1 is the same as reduced one, and the same holds on this side. And we have this convolution here, and this convolution maps this Fp to Fq, where P and Q are conjugate. So they are isometrically anti-isomorphic. In particular, all these guys here in the middle are star Banach algebras, and these are star algebras. These are the standard objects here. And the theorem we were aiming at, so there are no criteria for the simplicity of this reduced guy here, and we wanted to generalize this to this picture. But in order to do that, it would be good to have a reduced version of our universal Banach groupoid algebra, but it's hard to think of a regular action. I mean, there is no universal Banach space to act on. So instead of we took a different approach. I mean, so this these reduced algebras can be also characterized as those that can be embedded to C0 of G. So this vanishing at infinity continuous function. So this is just the completion of our this basic algebraic set. So this lemma is known to hold for LP algebra, I mean for sister algebras. So this is this J map of Jean Renaud, and we can kind of prove the same for our Banach groupoid algebra. So what is it? So this inclusion of the CC of G into C0 of G extends to a contractive linear map of our groupoid algebra into C0 of G. So, and moreover, the kernel is an ideal in F of G. So by an ideal, here I always mean closed-two-sided ideal. So this is an ideal in a category of Banach algebras. So for these LP operator algebras holds the same, and this kernel here coincides with the kernel of the regular representation. So this inspires us to coin the following notion of the groupoid, reduced groupoid Banach algebra. But what is important here is that we have this commutative diagram, so everything agrees with everything. So all these algebras, I mean, all these spaces are completions of CC of G. These are contractive homomorphisms. These are just linear maps, but they are injective. So we may view these things here as functions living on the groupoid. And this is a very useful thing that allows us to study the structure. And in fact, I didn't say that, but this F follows the tradition introduced by Hertz in 1973, who kind of looked at the group Banach algebras and a group LP operator algebras. So he called those elements of these algebras, he called pseudo functions. That is why this F for functions. And we can see for the reduced objects, I mean, we may view them actually as functions on G. And having that, we can analyze the structure of this, because then we can transfer properties of the groupoid to the reduced objects. So we have this, now the simplicity criteria will follow from this even more general theorem, which can be used to study the general structure of the ideal structure of our algebras. So for simplicity here, I will assume that the groupoid is Hausdorff. So the following conditions are equivalent. So the intersection property says that whenever we have an ideal in our groupoid Banach algebra, which does not intersect this C0 of X that sits in there, then this ideal is contained in this kernel of this regular representation. So equivalently, every representation of this universal guy, if it is injective on C0 of X, then it factors to an injective representation of the reduced algebra. This implies the same for all these LP groupoid algebras. This, of course, implies this for some of them. And whenever you have this property for at least one LP groupoid algebra, then we can show that this implies that the groupoid is topologically free. This is also kind of standard notion, this for group actions. So what does it mean? It means topological freeness says that whenever we have a bisection which is non-trivial, meaning not lying in the unit space, then the induced partial homeomorphism has very few fixed points from the topological point of view. So the set of fixed points has empty interior. So this is not exactly free, but topologically free. And this implies 1. So in this way, I mean, this theorem is very well known for in the case of sister algebras. And now we managed to generalize this to the framework of Banach groupoid algebras. And this, as a corollary, gives the promised simplicity criteria. So assuming this above, the following conditions are equivalent. So the reduced Banach groupoid algebra is simple if and only if all these LP operator groupoid algebras are simple, if and only if at least one of them, and if and only if the groupoid is minimal. And minimality of the groupoid is also a standard thing and natural thing, so this means that there are no non-trivial open G-invariant sets. So G-invariance means that whenever the arrow starts in a set, then the range is also in the set. So the groupoid cannot be decomposed into two non-trivial parts. So So this currently, in fact, solves the problem posed by a number of authors, Chris Phillips, Sana Spuya, Martina Lupini, and Eusebio Gardella. So this was like one of the main obstacles for this theory to be pushed farther. So I hope that having this, I mean, now this is promising, and this might be like an impulse for the further development, and there are like immediate applications of this. I mean, so the simplicity of this LP version of Kuhn's algebras, Phillips proved by some ad hoc methods. This we get for free because we know very well the groupoid model for Kuhn's algebras. We have groupoid models for a number of algebras, so now we can, for graph algebras from Kuhn's, for Kuhn-Krieger algebras, and for many other constructions that we know from sister algebra theory, that we can now apply it in this context, producing possibly some also interesting Banach algebras. And is my time up? I think so. So thank you.
So thank you very much, Professor Kwaśniewski. Now I think we have time because you finish 1 minute before, so thank you. So you have more time for questions, remarks, and maybe some other important business in mathematics. At least there is a once. Oh, please. Oh, even two, please.
Thank you very much for a very nice talk, Bartosz. I just wanted to check, so the significance of these theorems seems to be that you basically say for your new setting, right, everything reduces to the same situation as for C-star algebras, right?
Yes.
Because basically in condition 3, you can pick p equal to 2.
Yes.
And that's the,
yes.
The classical,
exactly.
the C-star
yes.
case, right?
Yes.
Thank
yes.
you.
Thank you very much. You should wait. Similar question. So, some more.
I can ask a question myself, if you want to.
I have question, but I wait for, I even have two questions, but I wait for no question more. So my first question is very simple. Each groupoid is group. No,
each group is a group.
Each group is groupoid.
Yes.
So what your theorem saying for group? This is new result? Or?
I mean, so if you take a group, then this result is no good because in a group case, I mean, so if you have a group, so it acts, I mean, if you want to view it as a groupoid, then it acts on a single point, and this is never topologically free. Then, I mean, so then this criteria will never work. I mean, but for group actions, this will work. And also, I mean, this is like if and only if result if you want to look at the universal objects, like not reduced, but universal object, because this intersection property tells you that that the universal algebras, not reduced, but universal, are simple if and only if the groupoid is topologically free and minimal. Mm-hmm. So in case of group, minimality is for free because there is only one point, but there is no topological freeness at all.
Thank you. And some question. I have more important question because there is still open a very nice problem of Dixmier for groups, but maybe also for groupoids. This so-called unitarizable case. So Dixmier showed that if, at least assume discrete group, not topology, that if discrete group has Banach mean, that invariant Banach mean, that's called amenable group, yes. That every bounded unitary Hilbert representation is unitarizable. So there exists basis that operators are unitary. And Dixmier question is vice versa. If we know that for group, every uniformly bounded representation is unitarizable, it that imply amenability. So my question is, that maybe because you have a larger object, maybe the Dixmier problem you can solve for some class. I have some result, and also Pizier, Varopoulos. There is a plenty of people. What you call universal, we call tensor algebras or tensors Littwood function. This is in lecture note by Pizier, similarity problems, which is connected with the famous similarity problem, like inverse of von Neumann inequality. So did you think about this question? Because you have, like group, you have unitary representation, uniformly bounded, Hilbert.
So, I mean, so in general, amenability question is a different question that we wanted to attack. So this piece was missing, and it was like a very important piece because, I mean, this is like a basic fact for sister algebraists, what I just showed you in this more general context, and we needed to like use different tools to prove it. But amenability for groupoids is even trickier than the group amenability for...
No, I know there is Renault lecture notes when is everything done.
Yeah.
So no, but my question, because you have reduced and you have full sister algebra, tra-la-la-la. So you have, but my question is if you consider...
No, I mean, so I just learned a lot about this. I mean, so kind of this theory is new to me. I mean, so there are plenty of papers that are not even published. They are very hard to read, so I wanted also to understand, put things in order. So this is like a first step in this direction.
Okay, thank you. We can discuss.
I don't know much more.
We are in Poland, so it's easy to discuss with you later. So at least that subject is interesting, and if no more question, we would like to thank to Professor Kwaśniewski.